Good. So I got your 2 pages here. Which one do you want to start on?
Can we start on the one you're on right now?
Sure. Shall we start on 37?
Yeah.
Okay. Find the horizontal asymptotes and the end behavior. Those 2 things mean the same thing. A horizontal asymptote is what f of x goes to as x goes to infinity. Okay?
Okay.
Now, whenever x goes to infinity and you have a rational quotient, it kind of depends on let's cover the 3 situations. What happens here if x goes to infinity? What's this reduced to?
Just x, right?
So
No.
what So what happens when x goes to infinity? F of x goes to
Infinity.
Okay. Now, let's switch it up and give the other situation. There's only 3 possibilities. What happens to that?
That'd be 1 over x. And so it would go to 1 or 0?
0. If x goes to infinity, that thing goes to 0. Okay? So we covered when the numerator is greater than the denominator, and we've covered when the denominator is greater than the numerator. Well, the only other situation is where they're the same. When they're the same, the limit is the ratio of the coefficients. So let's say I had this. The limit of that as x goes to infinity is 3 over 2. Okay? So that's the only 3 situations you have. And it doesn't matter what else is going along for the ride. In other words, that can be 17x, that can be 391x. Does not matter. The only terms that matter are the highest degree polynomial in the expression. You can ignore everything else. So in 37, the numerator, what's the highest degree?
The highest degree is x squared.
What's that? 37.
X to the 6th.
4x to the 6th.
Oh.
In the denominator, what's the highest degree?
6x to the 6th.
Okay, the exponents are the same. What is the horizontal asymptote?
4 over x. 4 over 6, sorry.
Yeah, it's actually y equal to 2 over 3, which is 4 over 6. And that's the end behavior also. In other words, as x goes to infinity, f of x goes to 2/3.
Okay, so the end behavior you would just put
y
in,
is the same as f of x. What were you saying?
for the end behavior model, you would just put in like the 4x to the 6th over 6x to the 6th?
Yes, nothing else matters.
Okay.
It's only the highest degree polynomial that matters. Okay? So you don't care about this 2x minus 8. You don't care about this 8 minus 5x squared. Immaterial to end behavior. End behavior is only dependent on the highest degree polynomial. So, in 38, what's the numerator's highest degree polynomial?
3x to the 6 over, and then the bottom is x to the 4th.
Okay. What's the horizontal asymptote there? Or actually, let's talk about limits, because I noticed in your second sheet you're getting into limits now.
Yeah, we have a quiz on limits tomorrow, so...
Okay, what's the limit of this as x goes to infinity?
As x goes to infinity, it's... is it 3?
No. The numerator blows up more than the denominator does.
Okay, so it's just infinity.
Yeah, whenever the numerator's degree is higher than the denominator, then as x goes to infinity, it's going to go to infinity. It may go to negative infinity. In other words, if you had something like this, as x goes to infinity, I would actually say that that goes to infinity also. Okay? So there's only 3 cases you have to memorize. One is where the exponent is bigger in the numerator. That's always going to infinity. The other is where the exponent's bigger in the denominator. That's always going to 0. And the third is where they're the same, and that's always going to the ratio of the coefficients.
Okay.
Okay?
So that's when x is approaching infinity, right? That's the only case where that's true?
Right.
Okay.
Right. All of these, though, talk about in behavior and asymptotes. Well, these two things kind of mean the same thing. In other words, a horizontal asymptote is what does y, or f of x, approach as x goes to positive infinity and negative infinity. That's also the answer to the in behavior. When they say in behavior, they mean what happens to f of x as x goes to infinity and negative infinity. So these two questions are the same thing. 39. What's the numerator's biggest degree?
The numerator's biggest degree is 4x to the 3rd.
And the denominator?
Is 6x to the 6th.
Is that a, yeah, that is a 6? Okay. So what happens as, what's the limit of this as x goes to positive infinity?
As x goes to positive infinity. Goes to 0?
Good.
Huh, yay. Huh.
Just always remember that if the bottom blows up, it goes to 0. If the top blows up, it goes to infinity. You know what I mean by blowing up?
Yeah, of course.
That's what it means to go to infinity, is you blow it up without limit. So that goes to 0, so that's the horizontal asymptote, is y equals 0. And the end behavior is, as x goes to infinity, we go to 0. As x goes to negative infinity, we go to 0. In other words, it doesn't really matter. This thing reduces to 2 over 3x to the 3rd. Okay?
Okay.
So if I want the limit of that as x goes to negative infinity, well, the bottom still blows up.
Okay.
Still goes to 0. Now, you could make an argument that if I have this situation, then that's going to x to the third, and as I go to negative infinity, this whole thing goes to negative infinity instead of positive infinity. So the power of your final exponent could make a difference. If I graphed y equals x to the third, you would see that as x goes to negative infinity, y goes to negative infinity. So it's not always 0, positive infinity, but sometimes it's 0, positive infinity, or negative infinity, or some number.
Okay.
Okay. What happened?
I don't think we need to do the rest of them on that page if you just want to go, the rest of them in that section if you just want to go down to 43.
Okay, I can certainly do that. Let me just take a quick look here. That one goes to infinity. In behavior is infinity. What's this one go to?
That one goes to...
The horizontal asymptote.
The horizontal asymptote's 4.
Good. What about this one over here? Horizontal asymptote?
Is 0.
Good. Find the vertical asymptotes and describe the behavior or the limit of f of x to the left and right of each vertical asymptote. Okay. Where's the vertical asymptote on 43?
Vertical asymptote. I don't know.
So whatever makes the denominator 0.
So 2.
That's how you graph these manually. Is you start. That's the initial step. Is you find out where the vertical asymptote is. Now, to find out the end behavior, remember this is f of x. And this is x. What's the horizontal asymptote on 43?
Is
powers are the same. That's x to the 1. That's x to the 1. The ratio of their coefficients is 1.
So 1.
There's my horizontal asymptote at y equal 1. Okay? Which means the end behavior is what? As I go to positive infinity, what does y go to?
1.
And as I go to negative infinity, what does y go to? Remember, that's the definition of horizontal asymptote. It's whatever you go to as x goes to both positive and negative infinity. So it's 1 in both situations. If I graph this, it's a hyperbolic function like that, and down here it looks like that. You can see from the graph that as x goes in this direction to positive infinity, y approaches the line y equals 1. As x goes to negative infinity in that direction, f of x also approaches the line y equals 1. And you can see why. We have x over x minus 2. What if x were 100? That's what we get. That's close to 1. What if x were 1,000,000? That's what we get. That's even closer to 1.
Okay.
So as x gets infinitely large, f of x gets closer to 1. We can see that happening. And the same thing on the other end. In other words, if I make both of these negatives, we got negative 1,000,000 over negative 1,000,002. Well, that's close to a positive 1, right? In other words, that's like 0.99999, which is what that's doing. on the left-hand side there.
Right.
All right. All right, where is the vertical asymptote on 44?
The vertical asymptote. That's a little harder because you gotta...
Yes, it is. What do you have to do to the denominator? There's a hint.
Okay, so you have to factor it.
Okay, factor that for me.
Okay.
How do you factor that? What's the second step after you split up the x squared into x and x?
Well, what I did was I did the California method or
Whatever
whatever
method works for you.
So I got x minus 3 and x plus 5.
Good. Okay, now tell me the vertical asymptotes.
Vertical asymptotes are 3 and negative 5.
Good. And the end behavior, and the end behavior is actually easier to see if I put it back together again.
Okay,
see
yeah,
why?
true. Yeah, because you can see the degrees.
Yeah, exactly. So as x goes to positive or negative infinity, what does f of x go to?
2.
Very good. I think you got it.
Yes. We can go on to the second page if you want.
Well, hold on a second. I want to make sure you got it.
Okay.
Okay. I think you do. All right, let's go to the second page just because we're running out of time. And I think there's probably stuff on there that you want to talk about.
Yeah, lots of stuff with limits.
Okay. All right. As x approaches negative 1 from, is that a minus sign there?
Yeah. Wait, no.
Yeah.
Oh, yeah, it says negative 1,
This is
yeah.
a positive sign over here. So what's the limit as x approaches negative 1 from the left side?
So don't we have to graph these, or do we not have to graph them?
You don't really have to graph it. We can graph it if
Okay.
it helps understanding it. Start from this. Whenever you're graphing a piecewise function, start from the right side and the top. In other words, what happens to the left of minus 1? Well, I have a parabolic function that opens up and would normally look something like this, but I only have the left part of it.
Okay.
In other words, it doesn't go through that axis. The left side of it might look something like, let's see, this is the last problem. In other words, let me graph the function as I think it would look if it was the whole thing. Okay, well, we only want that piece of it. This piece right here. Everything else gets erased. Okay? So that's the first part of the function. Now, as we approach this from the left side, this way, what does f of x approach? Yeah, what's that value right there?
It's like 7. right? Or 5. Does it approach 5?
Oh, you were correct. 7 is correct. In other words, you do plug in minus 1 for x, square it, you get 1, times 2, you get 2, plus 5, you get 7. That point is 7.
Okay.
And even though it's an open circle there, because it's only less than minus 1, where this function applies, the fact is that if you follow a line on this function, in other words, if you start approaching negative 1, you end up at minus 7.
Okay.
Even though x is not minus 7 at negative 1. What is x at negative 1?
5. 4.
Middle part.
Oh, at negative 1 is 3.
Okay. So, from at negative 1 itself, closed dot, that's what its value is at negative 1.
Okay.
What is it to the right of negative 1? This function here. That's also parabolic, opening up, but going through the point 2. So, if I want to know exactly what it's going to be at negative 1, I would plug in negative 1 for x. I get 3 plus 2 is 5. So, right there is where it starts with an open circle because it's greater than. So, there's an open circle at 5. And it's a parabolic function that would be graphed like this, essentially. Now, make sure you understand every single thing that I've drawn on there.
Yeah, I do.
This is actually a closed circle. Excuse me, that closed circle is 3. Okay, I've drawn this a little bit incorrect. Let me draw it again. At negative 1, it's 5. And it goes through 2. So that's what the graph looks like. Open circle, closed circle. Okay? This is an excellent illustration as to how to do limits. As I'm approaching negative 1, from the left, what does f of x approach? What is this number?
5?
No, this number here. As I'm approaching it from the left, look at these arrows.
Oh, okay, 7, yeah. Okay, that makes sense.
Okay. As I approach it from the right, what does it approach?
5.
Exactly. And what is it at 3 or at negative 1?
3.
Yes. So here's the classic case for limits. As you approach it from the left, it's 7. As you approach it from the right, it's 5. So what is the limit at negative 1?
Is it 3? Or, okay, since all of them don't match up, it's undefined, right?
You don't need all 3 of them to match up, you just need 2 of them. The only 2 that have to match are those 2. In other words, the limit from the left has to match the limit from the right, or else it's undefined. That's just flat out right. In other words, if I drew this case, this is even stronger. As this function approaches 3 from the left, what is its limit?
1.
As it approaches 3 from the right, what is its limit?
1.
What is the limit at 3?
1. Okay, I was wondering if you were asking about the top dot or not.
Well,
Okay,
the top dot is there. In other words, f of 3 is 4. I want to know what f of 3 is, it's 4. But the limit as it approaches 3 is not 4. In other words, the limit only exists if from the left it approaches the same number as it approaches from the right. And in this case, that number is 1. So that's the limit. The limit of f as it approaches 3 is 1, regardless of the fact that f of 3 is 4.
Okay.
So this is a very important concept in limits, that situation right there. And we have a very similar thing with our problem, and that certainly the limit from the left does not approach the limit from the right. They're not the same number, so it's undefined. And f of -1 is 3. It's neither 5 nor 7. It's 3.
Okay.
Okay, so f of x as we approach -1 from the left side is what?
7.
From the right side?
5.
What's the limit as we approach -1?
Undefined.
And what is f of -1?
3.
You got it. If you understand those 4 questions, you understand this stuff.
Yeah.
As we approach 2, over here, there's our function. What does f of x approach as we approach 2?
0. No, and as we approach 2, infinity, right?
No, plug it in. Plug 2 in.
Okay. 2. So 2 squared is 4 times 3 is 12. And then 14?
Yes. 14 is the answer. In other words, I'm only looking at this part of the function over here. There's nothing strange going on at all. If at 2, this point is going to be 14. In other words, you just plug it in to whichever part of this piecewise function applies. What is f of -3?
F of -3. Okay, so 3 squared is 9 times 2 is 18 plus 5. It would be 23.
Very good. Use the graph to estimate the limits. Hold on. What is the limit? G of x is the vertical axis. We can see that we have a strange looking piecewise non-continuous function. So what does it approach as we approach 2 from the left side?
1.
From the right side?
1.
What's the limit of this function as x goes to 2?
1.
What is g of 2?
3.
Good. Very good.
She's got me doing all this crazy work, and I don't think, like on number 31, I feel like you don't need any of it, because it's when x goes to infinity, so since the bottom blows up, it's just 0.
Well, not really. Here we have a mixture of trig functions. Well, you are right. In other words, whether that's a trig function or not, we've got x over x squared. So the bottom's blowing up faster than the top. but that's going to go to 0 exactly. And the fact that the sign of x is in there, well, the sign, as x gets big, the sign of x actually bounces back and forth between 1 and negative 1. If you remember what the sine function looks like, it looks like this. So as you go to infinity, it just keeps vacillating between 1 and minus 1. So the fact is that that's always going to be between 1 and minus 1. Well, this is going to rule. This goes to infinity faster than this does. So this goes to 0.
Okay.
Another way to do 31 is to factor an x out from the bottom, and then cancel it with the x on the top, so you end up with sine x over 6x minus 1, and then it's real easy to see that the bottom blows up.
Okay.
Well, you only had a half-hour scheduled. Do you want to do more than a half hour, or do you want to stop?
I think it makes sense to me because I understand the infinity thing, and that's what I was struggling with, but I know it can only be infinity, 0, and 1, so that makes sense.
Right. It seems like you do get it from so far from what we've looked at. So.
Yeah. So I think we're good.
Okay. All right, Aspen, we still on for Wednesday at 7?
I actually was going to tell you about that. I have work that night, but I can do Thursday.
Okay. I will cancel the Wednesday session. And now, hold on before you leave. Thursday's at 6:30, I believe.
Yeah.
Okay. So I'll talk to you Thursday at 6:30.
Yep, sounds good.
All right, Aspen. Bye-bye.
Bye.